Hello everyone, I am back again in my second tutorial, that is solvation of the system we have just generated in the previous tutorial. So we will solve it our system in water. So for that we need to use the commands set space water, and then there will be a space within third bracket atom select top water. So the top structure that has been loaded, all the atoms are selected for water solvation. Next command will be measure a single space, then min max, and after min max there will be a space dollar water. So what we have got here, the minimum and maximum coordinates for all the three axes, that means x, y and z axis of our system. The left three values are the minimum coordinates of x, y, z, and the right three values are the maximum coordinates of the x, y, z. Now package require solve it. So we'll use the solve it. There is a problem. Just a minute. Package space require QUIRE. Let me check. I think it's, what was the problem? Okay, let's try and solve it. Okay, it's done. So we'll use the solvate package to solvate our system. That's why we've used the command package require solvate. Now we'll use the command to solvate the system. So solvate adrb underscore popc. It means the pdb, so .psf and the pdb file. So adrb underscore popc .psf, and then a space adrb underscore popc pdb. So essentially we're trying to solve it, both of them we have just generated in the previous tutorial. And then there will be a space, a small hyphen, and then O stands for output. The output file will be a space, the name of the output file will be adrb underscore popc and underscore water, and then underscore temp. So we're naming this as a temporary water file, I mean solvated file. So it will essentially generate a pdb and a psf file. Now a space, small hyphen b, the b factor, and then a space 1.5. So we are keeping the b factor 1.5, and then there will be a slash, a small hyphen min max. So we are using the minimum and the maximum coordinates we just got using command, and we'll try to put all the min max values over here. So essentially as we have the minimum x value minus 37 point something, so we are keeping here to be safe minus 38. Same goes for minimum y, that is we are keeping minus 38, and for minus for minimum z, as there is the coordinate value minus 27 point something, there is something, so we are keeping it minus 28, minus sorry, not 28, 29 to be safe. and same goes for the maximum values of the x, y, z coordinates. So 39 and then 39 and then 29. So we'll close the command with 2 brackets. So let me check. So minus 37, minus 38, minus 37, minus 38, minus 27. We are keeping this 29 as there is the value minus 27.9, which is very near to minus 28. That's why we have kept here minus 29. Same goes for the positive values, 27.8 or something. So we have used 29. And now we will hit enter. There is something some problem. Okay, so I think I haven't used one bracket. Yes, there's a missing bracket after min max. Yes, so this is the problem of command line operations, because you have to keep all the time your mind highly concentrated, so that there is no mistake in between words, in numericals and all the parameters and like that. It will work finely. So we'll hit enter, and so Solvation has started. You will get all these messages in the ticket console when Solvation started. Generating structure, segment complete, and you will get this final command, the message that is solve it completed successfully. So we have now solvated our entire system as a temporary file of ADRB POPC water, because we need to modify it a lot. We need to remove again the bad water contacts, and then we'll get only the final file. Sorry. So for better understanding, okay, we'll do that later. Now we need to remove all the bad waters creating steric hindrance with the protein and lipid molecules. For that, we are using the command so we'll use set space all, and within bracket atom select top all. So essentially we are selecting all the atoms of the loaded top structure, and then you can see atom select 45 is the message. And now $sign all, as we have previously set the all as a function of atom select top all. So we are setting the beta as 0, beta value 0 for all the atoms of the top loaded structure, and then set cell text just we did previously in our first tutorial. We are doing the same thing for removing the bad water contacts. So the command will be set, and then there will be space cell text space inverted comma seg id wt1 to wt99 space and space same residue space as abs x on the x axis. We are trying to keep the value less than 25 and closing it with the inverted comma and then enter, hitting enter, and then set space cell within third bracket atom select, and there will be a space stop space a $sign and then cell text, closing the command with third bracket and then we'll hit enter. Dollar cell and then set beta 1. So we're keeping the beta parameter value 1. Now we'll set the bad water and in the third bracket we'll use atom select top within inverted comma name OH2 stands for hydroxyl and beta greater than 0. So they have mentioned in this command them as the bad water contacts. And the next command set seg list, we want to get the seg IDs over here, and in the third bracket we'll use bad water get seg ID and then we'll hit the enter. So here are the segment IDs of the bad water molecules creating steric hindrance with the protein and the lipid molecules and atoms. Then set res list, so we want to get the res, that means residue IDs over here. So with the third bracket bad water get res ID, third bracket closes the command and then we'll hit enter, and here we get all the residue IDs of the bad water molecules. We are going to delete. Now our next command will be mol delete all, to delete all the previously loaded structures in the window, and then package a space require PSF chain. We have used this command several times in our previous tutorial, and then preset PSF. Now we will use as we have done previously, read PSF ADRB underscore POPC underscore and then water underscore temp dot PSF. So we are loading the PSF file, the protein structure file, and then we'll use coord PDB to load the PDB file ADRB underscore POPC underscore water underscore then temp dot PDB on top of the protein structure file. We'll hit enter and load it. Now we'll use the commands to delete all the bad contact waters. For that, for SEH, a single space, seg ID, as we have all the seg IDs of those water molecules, and then a space $seg list lipid. Same res ID will be a $res list lipid. So we are directing the seg ID as seg list, sorry, not lipid, seg list, because we have used seg list for the bad water molecules over here. Same goes for res ID. We are directing the res IDs as res list. Within first bracket, del atom seg ID, res ID, both carrying $sign at front of them. Hit enter, all the molecules will be deleted. I mean, all those water molecules will be deleted. Now we'll create a PDB and a PSF file over here. So write PDB ADRB POPC, and we will use a single W, stands for solvated structure, and .pdb extension, and we'll also use the command write PSF ADRB underscore POPCW .psf to generate the protein structure file, and it is generated. So we have now a PDB and PSF structure file for the solvated system. File delete, will delete the files that we do not need anymore. So ADRB underscore POPC underscore water underscore, and there will be temp dot PSF. We do not need it anymore. And same goes file delete ADRB underscore POPC underscore water temp dot PDB. Enter. So now we have the solvated system, and we will check whether all the extracellular and intracellular domain has been solvated. If not, then we will repeat the step using higher values of Z. So we'll load so let's start from the beginning. So downloads, under that we have the MD3 and MD subfolder, where we have the ADRB POPCW PSF file, and that's it. We'll load it in the VMD. So after selecting, we'll hit open and then load. So the structure file has been loaded, and now the PDB file we are going to load on top of the structure file. So load. Now to visualize the water molecules on top and below of the lipid bilayer, we need to change its representation. So firstly, protein, new cartoon, and we're selecting red color for the protein. So create replicate, res name POPC, this one for the lipid bilayer, and it can be visualized with lines, and we're choosing the color yellow, and again we are keeping water as lines, and we are selecting the color cyan for the water molecules. Apply. So now let's check whether the extracellular and intracellular domains are completely solvated or not. If not, we have to repeat what we have done just now to solve it more perfectly. As you can see that the cytosolic and the extracellular domain, a major portion of two domains, have not yet been solvated. So I will stop here, repeating the same commands using a higher plus Z and minus Z value, as the Z coordinate is basically the coordinate representing the height of our system, that means the height of this lipid bilayer. So essentially, if we increase the value of plus z and minus z, keeping the x, y values same we have used in the solvation, in the solvate package, then it will add a few more layers of water on top and below our structure, and so that our extracellular and cytosolic domains will be completely solvated. So I am back with my perfectly solvated structure, and now we'll ionize the system, our system, using add ions auto ionize plugin. So in this auto ionize plugin, you can see that the input files are already loaded, PDB and PSF. We'll keep the output base name as ADRB underscore POPC, W stands for water, and then I stands for ionization. And we want to neutralize our system with sodium chloride, and we'll keep the concentration of sodium and chloride ions in our system 0.14 mole per liter. And all the other parameters will keep them default. So auto ionize, as you can see in the TK console, that our system is now solvated and ionized. So we are absolutely ready to run our system in a molecular dynamic simulation and energy minimization that we will be doing in our next tutorial, in the tutorial 3. So for today we are done, and thank you.